So now that we've had some practice with our new parts, holes, vertical asymptotes, and horizontal asymptotes, we're going to continue along here and graph some functions, pulling it all together simultaneously. So here we have a rational function, and we're going to list all the characteristics and create the graph. So the first thing we always do is we want to make sure we create the factored form. So the numerator, I can factor out a 2, and that leaves me with x squared minus 9. And we should all recognize that x squared minus 9 is in fact a difference of squares, so we can factor it a little bit further, x minus 3, x plus 3. And then the denominator here factors like a traditional quadratic would, and I'm going to have x plus 1 and x plus 3. So we're going to run through stating all of these attributes. The first thing is the domain, and when we think about the domain, what we know is the denominator can't be 0. So we don't want to cancel anything yet because I have 2 factors in the denominator, and neither of those are allowed to equal 0. So here we're going to say that x cannot equal -1 or -3. Writing that in interval notation, that would be -infinity to -3, union -3 to -1, union 1 to positive infinity. So that is my domain here. Now, do any factors cancel out? Do we have a common factor in the numerator and the denominator? And we do. X plus 3 reduces away. Okay, so since x plus 3 cancels, what we know is there is a hole at the value that would zero that factor out. So there's a hole at x equals -3. And because this has reduced out, we have our reduced version. F of x is now equal to 2 times x minus 3 over x plus 1. So I can't plug -3 into the original function to find the ordered pair for my whole because it would give me 0 in the denominator. So what I'm going to do is I'll plug it in here. F of -3 is 2 -3 minus 3 over -3 plus 1. That simplifies. In the numerator, I have -12 over -2, which is -6. Pardon me? -12 over -2 is positive 6. We have -12 in the numerator over -2. So positive 6. So what we know is there's a hole at -3, positive 6. And we write that hole as an ordered pair. Okay, so for everything else that we do, we're going to use the reduced function. My reduced function, I'll rewrite it. F of x is 2 x minus 3 over x plus 1. And we could multiply that back out if we wanted and say 2x minus 6 in the numerator. It would still be the same thing. So the vertical asymptote, that's going to come from the factor that is remaining in the denominator. So again, rewriting that, we've got f of x equals 2x minus 6 over x plus 1. And since x plus 1 remains, we end up with x equals -1, and that's my vertical asymptote. And so one thing you're always going to notice is that value from the vertical asymptote and the value from your holes, those are going to be occurring in your domain because those are both undefined values that the graph will never touch. All right, For the horizontal function, we use our comparison test. In our second video in this unit, we talked a lot about that. But this is the same as 2x minus 6 over x plus 1. And what we notice is the degree of the numerator, it's linear. We've got a little invisible 1 there. And the degree of the denominator is also linear. And so if the degree of the numerator and the denominator are the same, then we say y equals a over b. And a and b come from those leading coefficients. So in this case, I'm going to get y equals 2 over 1, and 2 over 1 just simplifies to 2. All right, we haven't had any practice finding x-intercepts and y-intercepts yet, but we found x and y-intercepts for polynomial, linear, quadratic functions, and it's really the same thing. In order to find x-intercepts, you do y equal to 0 and you find the x value, and to find the y-intercept, you let x equal 0. So letting the function y, f of x, be 0, we would say 0 equals 2, I'm going to use the factored form of this here, 2 times x minus 3 over x plus 1. So solving this for x, well, we can treat that 0 like it's over a 1, and then we would cross multiply here. So 0 times anything is going to go away. And so when I do that cross multiplication, what I'm going to end up with is just the numerator. 0 equals 2x minus 3. So my x-intercept occurs at that value that would zero that out. My x-intercept's occurring at positive 3. So my x-intercept, we write x-intercepts as an ordered pair. I have 3, 0. My y-intercept, that occurs when we let x be 0 and find y. And we can always just plug 0 into the function. 2 times 0 minus 6 over 0 plus 1. And the first terms zero out, we end up with the ratio of those constants, negative 6 over 1. So the y-intercept occurs at negative 6 over positive 1, which is just negative 6. So I have 0, negative 6 here. So now we're going to need to graph this. In order for us to graph this, we're going to plot our vertical and horizontal asymptotes first. So we have a vertical asymptote at x equals negative 1 and a horizontal asymptote at y equals 2. So x equals negative 1 is a vertical line, 1 unit to the left of the y-axis, and y equals 2 is a horizontal line 2 units above the x-axis. I have 2 ordered pairs here. I can plot my x-intercept at positive 3 on the x-axis and my y-intercept at negative 6. Down here on the y-axis. So I've got negative 6, 0, negative 6. And 3, 0. And then we also mentioned that we have a hole. The hole occurs at negative 3, positive 6. So negative 3, positive 6 is right there. So, you can spend all day making a table of values, plugging a number in, getting a number out. Some other points we might have on our function: -2, +10, -5, +4, -9, 3. And that would give us a little bit of a better idea of what our curve looks like. But essentially we get a graph, and use your calculator to help you check, that curves up and bounds the x and y asymptotes in the upper left and lower right corners. And we're done. And so you just want to make sure, if you go to plot this in your graphing calculator, that you use your parentheses correctly. So if I were to write this in my y1, I would use parentheses 2x squared minus 18 divided by, and then I would use my other parentheses, x squared plus 4x plus 3. Without using the parentheses to group the entire numerator divided by the group of the entire denominator, you're not going to get the correct graph. So make sure you can do that, because your calculator is a great tool that you're always going to have with you in your math classes. So we have another example here: rational function f of x equals 4x plus 6 divided by 2x squared plus 5x plus 3. I'm going to encourage you right now to pause the video and find all of the attributes like we did on that last example. See if you can do it on your own, and then I'm going to run through the solutions. So that would be finding the domain, a hole, which we call a discontinuity, which occurs when we reduce the function, we cancel a common factor, vertical and horizontal asymptotes, x and y intercepts, and then also creating the graph. And you'll notice, on this one, our last example, I had little hints written out beside everything that we were doing. This one, we're trying to make sure we understand all of these steps a little bit better, because, when we take the test, we're not going to have all of those hints written down beside us. Okay, so we want to find all these attributes. So assuming you've paused it and worked it out on your own, I'm going to work through this one a little more quickly. First thing we do is factor. We can pull out a 2, which leaves me with 2x plus 3 over the denominator factors, and I have 2x plus 3, x plus 1. So of course we notice something is going to reduce out here. I'm not going to reduce that out until after I've found my domain. And my domain says that my x values that would zero out the denominator, those need to be omitted. And if I solved each of those two factors equal to 0, I would get that x cannot equal -3/2 and -1. So my solution for domain in interval notation would be -∞, -3/2, union -3/2, -1, union -1 to infinity. All right, now as I mentioned, we have a factor that's going to cancel. So the factor that cancels, I know I'm omitting -3/2 from the domain because it's going to be a hole. So there's a hole at x equals -3/2. Okay? Another thing I know is that since that -1 is also something that we're omitting, that's going to be my vertical asymptote. So the hole being at x equals -3/2, we plug that into our reduced version, which is 2 over x plus 1. So f of x equals 2 over x plus 1. In this situation, f of x equals 2 over -3/2 plus 1. That gives me a 1/2 in the denominator, which is multiplying by -2, I get -4. So my whole occurs at -3/2, -4. So I have my reduced version here, and this is what I use for the rest of my problem. So my vertical asymptote is my other undefined value. -3/2 was my whole, so x equals -1 is my vertical asymptote. My horizontal asymptote comes from using the comparison test. So I have 2 over x plus 1. The degree of my numerator is 0 because it's constant, and the degree of my denominator is 1 because it's linear. So, because n is less than d, my horizontal asymptote occurs at y equals 0. The x-intercept comes from that reduced numerator being equal to 0. And in this case, I would go over here and say, well, 2 equals 0. And 2 cannot equal 0. There's no x-intercept. And then the y-intercept is determined by letting x equal 0. So f of 0 equals 2 over 0 plus 1. And you'll notice it's just going to simplify to 2. So my y-intercept is at 0, 2. So now if I were to continue along and graph this, and I can make a table of values as I see fit. XY, or, XF of X using our more formal notation. I just said that I have a vertical asymptote at x equals -1. I said I have a horizontal asymptote at y equals 0, so that is on the x-axis. I only have one point to plot, 0, 2, so +2 on my y-axis. And then I have a whole, and my whole is at -3/2, -4. So that's -1.5 down 4 units. And then if we want more points to help us make a more accurate picture, of course we can always, go back to our original function and plug in x values and get out y values. You always want to make sure you go back to the original function here. When I say the original function, we're talking about 4x plus 6 divided by 2x squared plus 5x plus 3. So I can plug in numbers. If I were to evaluate at -5, I would get -1/2. At -3, I get out -1. -2, -2. 1, 1 is an ordered pair here. And maybe 3 +1/2. So I'm going to plot those points. -5 down 1/2, right about there. -3 down 1. -2 down 2. And you can start to see that curve forming. On the positive side, I might have 1 +1 and over 3 up 1/2. So you can see Here's the curve of my rational function, and it really does bound right up, getting infinitely close to those asymptotes, but never touching them. And remember, sometimes we can cross a horizontal asymptote, but you will never cross a vertical asymptote.